obviously. And if we choose x values less than 3, and again approach 3, 2.9, 2.99, 2.9999999, we see how the function value approaches 12 again. So basically we say that 12 is the limit, not the limit as you may never go beyond, but the limit as the aim towards which we can strive. So the term limit is obviously not very clear sometimes. In this case, in calculus, a limit means not something that sets the boundary, the forbidden other places, but the limit is considered a goal towards which some expression, the value of some expression tends. So as x approaches 3 from the left and from the right, as you can see in the graph, the function value approaches 12 again from both sides. So we say that 12 is the limit of the function when x tends towards 3. X tends to 3 or x approaches 3, and at that same time the function value approaches 12. That's our understanding of the limit. It's written lib of f of x. Instead of f of x, we can write the formula for the function. We don't have to write f of x. We can write the formula. Below the three letters lim, below lim, we write x tends towards, well, in this case it's x0, towards something. So x, this arrow is read as x tends towards x0 or x approaches x0, although if it's infinity, we can't say approach infinity because infinity cannot be approached. It's too far, infinitely far. And so the definition, that's a beautiful one. We call the number a the limit of a function if it is possible to find values of function as close to it as desired, if the x values are chosen close enough to x0, which sounds extremely non-mathematical. It sounds extremely vague. What does it mean? As close to a as desired. X values chosen close enough to x0. It sounds a little bit strange, and therefore above this we have the official definition using logic. So those who like logic and those who can understand this For the rest of you, probably we can do without. So what matters for us for practical use, this is not what I would do in an academical course, in the classical, in the academical university. In a technical university, I can afford to give you a vague definition of limit. In the university back there, I would do something else. I would do it differently. We would go through the formal, logical definition and proofs and all kinds of things. But for you, the practical approach is the one that makes more sense and is necessary. So we can say well, at least what we can see from that formal definition is that we can choose any number positive, but what we have in mind, what is not stated there, any number, even extremely small ones. And this is what matters here. We can choose any very, very small number and ask that the difference between the function value and this a value is less than this very, very, very small number I chose. And if a is indeed the limit, then we can find such x values close enough, very close to the x0 value, for which actually this inequality holds true. The approach we used, these things are called one-sided limits. So we can write, I can't help, I have to write. This is unpleasant. So we write, for example, x tends to 3 with a little bit, or with a little plus. X tends to 3 plus, it means, and we have this expression x squared minus 9, x minus 1, x minus 3, I think was this.
Yeah.
Yes, it was this. So this was what we found. It's 12. Of course, we saw experimentally. We didn't calculate anything. Well, I did. I used Excel to create those little tables. So I wanted to find some nice values to show you. X tends towards 3 plus means x tends towards 3, but x stays greater than 3. So from the right-hand side. So this is called the right-hand limit. The right-hand limit. All the limit from the right-hand side. And the other one, we can write the same limit of, well, I'll be short, towards 3 minus means x tends to 3, but x remains less than 3, so from the negative side. And we saw that in our case, both those limits were the same. In both cases, in our example, they were both equal to 12. So what this means is that we can use those one-sided limits to define the function limit just as well. I have actually stated it as a theorem. If those both one-sided limits exist and are equal, then the function has a limit. Then the limit of the function does exist and is equal to these one-sided limits. We could use this as a definition. If those two one-sided limits, if both of them are the same, are equal, then we call this value the function limit. But then we would need to prove that in this case, the previous statement which we used for definition is true. And then we would need to prove that. So there are basically two approaches. There are two approaches for this. There are actually more than two approaches towards definition of a limit. There are several definitions of limits, and basically mathematicians must be sure that they mean the same thing, that I won't get 12 by one definition and 10 by some other definition. So the mathematicians, of course, prove that all those definitions are equivalent. As for ourselves, we will just use these two. And basically, what we need is an intuitive understanding of this. So when x approaches a certain value, x0, for example, then the limit of the function is, which means the function value at this time approaches this whatever the limit a capital is. There might be several situations, as you can see, and I'm going to sit down again. Sorry. The function value could be the same. The function value could be the same as the limit if the limit exists. The function value could be defined but different from the limit. I'll just show you in a couple of moments. Or undefined or infinity. So sometimes the value, oh sorry, I have left it a. Too bad. It should be, instead of a in C, it should have been x0. I haven't noticed the change. I changed the notation. In C, if a defined or undefined or infinity, if a does not belong to the domain, it should have been x0, not a. Because otherwise, some people might ask, what kind of a? There's no a previously. What do you mean a doesn't belong to the domain?
It's x0.
Yeah, it should be x0. It should be x0. So the function could simply be undefined at that point. It could be infinity, the function value, and the limit could be something else. The actual value of the function does not necessarily have to be the same as the limit. For example, if you look at our function, you see that the graph looks like a parabola. Is it a parabola or not?
No.
Yes.
Because it's not funny.
Well, okay, there's a hole, a parabola with a hole, a broken
Okay,
parabola, a parabola with one point missing, the empty point. Right. Because if you transform that expression, if you factorize x squared minus 9, you can actually cancel out x minus 3, and you get a quadratic function. So a quadratic function with the exception of x value 3, which is simply taken out of this. So in this case, we can say the function is not defined at this point. So it's actually case C. The function is undefined at the point x0 equals 3, this example. Or sometimes it might be defined but different. For instance, remember those functions that we defined, that we described last time, the piecewise defined functions. We said, all right, that one branch, one part of this graph goes there, and then, okay, the other one goes somehow differently at this point. And I said, this is the empty point, this does not belong to the graph. The actual function value is here. By the way, in this case, the left-hand limit is one value and the right-hand limit is something different. So we can say that the function doesn't have a limit at this point for this value x. So this is one of possible examples. But for that parabola, I might say, for example, all right, we have this function, this nice function, all right, 3, 12, it's this. And I could say, all right, for all the values except for 3, the function values are as defined by this formula, but the function at 3 is, let's say, 6. So now I have a very strange definition of a function. The function is defined by that formula for all x values except for 3, and the function is 6 if x is 3. So I have taken one point out of the parabola and put it somewhere else. In this case, I would say the function is defined, but the value is different from the limit, because the limit is, we slide towards 12, so the limit is 12. So the limit of a function is the value towards which this function value tends or approaches. But sometimes, of course, it might simply be infinity. It's not always that the function limit has a specific value. It could be infinity. It could be infinity. In that case, we say that as x approaches x0, for example, the limit of the function or the function value tends to infinity. We can't say approach. Approaching means getting closer and closer, but we can't get any closer to infinity. So it is sometimes possible to say the limit equals infinity, but in that case we still say there's no finite limit. There's no finite limit. The limit is infinity, but the finite limit does not exist. In calculus, finite limits are extremely important. Well, I have to say that infinite limits are also important, but we have to make sure we understand which is which. And similarly, we could say x tends to infinity. For example, if we have a function 1 over x squared, if x tends to infinity, what do you think the function value tends to?
To infinity.
What does it mean x tends to infinity?
Tends to 0.
The function value tends to 0, yes. Why it happens is x tending to infinity means taking x values greater, even greater. Name me the greatest value of x you can imagine, but x becomes even more and more and more and more. So if I divide 1 by a very large number, I get a very small number. And the larger number it is, the smaller number I get for the quotient. And so if x is, well, I can't say infinitely large, but for very large values of x, obviously the values of this quotient will be very close to 0. So 0 is the limit of this if x tends to infinity. Visually, in graphs, we will look at graphs and see what those graphs look like in a few moments. We will do that. So now, continuous functions. The definition, a function is called continuous. Oh, sorry. I had to mention the fact that if a limit exists, when x tends to something, if a limit exists, then it's unique, one and only one. You can't say if x tends to 3, the function tends to 12 and also to 10. Not really. The one-sided limits can be different, but if I have the one unique limit from both sides the same, it's just one. I can't have two different limits for the same function tending to the same x. All right. Continuous functions. A function is called continuous if the limit is the same as the function value at that point. In other words, in this case, I would say this function is not continuous at 3. If x is 3, this function is not continuous. It's a discontinuity. A discontinuity. It's not continuous at this point. Informally, my own professor of mathematics at the university said, oh, you want to teach? Then you will have to tell them that a continuous function is one that you can draw on the board without taking the pen off the board, or the paper, or the pencil off the paper. They said, yes. And that's what I'm going to do. So, intuitively, a function is continuous if we can draw the graph without taking the pen off the paper. And any continuity means I have to stop, take it off, and then go on to sketch somewhere else. It could be like this, or it could be, of course, like this, tends to infinity, tends to infinity. There are two separate branches sometimes. See, can you imagine this?
So hyperbolas is also
discontinuous, yes. Because there's always one point, one value of x for which the function is not defined. So there's a discontinuity because 0, well, classically, 0 does not belong to the domain. So if it doesn't belong to the domain, then it's a gap, so it's a discontinuity. Exactly. So at some points, of course, the function is continuous, and then there are some discontinuities. Although very clever mathematicians have invented functions which are discontinuous at all points. Yes, it's strange. It's like a line with holes, or that's something difficult to understand. It's something like a line, but it has holes, but at the same time it's defined at every point, and it's not continuous at every point.
How it looks like?
It's very strange. For example, I could imagine that the function value is 1 if x is a rational number, which means it can be expressed as a quotient of two integers, and f of x is 0 if x is not a rational number.
It's like a program.
Yeah, exactly. So this graph actually consists of two parallel full lines full of holes, lines that are consisting of actually points and holes. So this kind of function. So it's discontinuous at every point, everywhere. At each point, wherever you look, it's discontinuous. So there are other functions constructed, other similar ideas, but these are extremely interesting, but they are more interesting for, let's say, theoretical use, not practically. For theoretical use, or perhaps for theoretical physics, and so on. All right, the two types of discontinuity. Type 1 is more or less the finite type of discontinuity. So both the one-sided limits exist and both are finite. So I I can approach this x0 value from either side, but the problem is that they are not the same. So they might not be the same when approaching from the left and from the right. So if I have right hand limit one value, left hand limit something else, then obviously there's a gap, and I can say that this is a jump discontinuity. I mentioned it last time, jump discontinuity, because this is what happens sometimes when we graph function that is defined piecewise by separate pieces. So it's a jump discontinuity because the function is continuous and then it just jumps to another value and goes on being continuous. Both these one-sided limits, they are finite. They are one. The right-hand limit is one value. The left-hand limit is another value. They both exist. They're both finite. They are not equal. So there's no limit for the function at this point. Limit in general, and the function is discontinuous, and it's type 1 jump discontinuity. Or, even worse, just like we had there, at this hole in the parabola, both the one-sided limits could be the same. But the function value is either the function is not defined there or it's somewhere else. So both the one-sided limits are the same, which means the function limit exists, it's that value, but the function value at that specific point, at the single point, is either non-existent, not defined, or somewhere else. So perhaps in this case, in my example on the paper, it's not defined, but if I put it somewhere else for that value of x, then it's somewhere else. And this is called removable discontinuity, because I can remove it simply by saying, all right, let's define f of 3 equals 12. If I redefine the value at that specific point, then of course, well, it's like I plug the hole, like in the bath. So I can plug the hole by simply redefining one single point. I can say, all right, the formula states that it should be empty, there's a hole. All right, let's give an extra definition. Let's add to the definition of that function. Let's say function of 3 equals 12. So I can, let's say, require that this hole be removed. The discontinuity can be removed. In this case, I can't really adjust anything. I can't fill it vertically because then it will not be a function. But in this case, I can simply give an extra definition. Well, let's suppose, okay, let's make it so that for x equal to 3, the function value is 12. Okay. And type 2 discontinuity involves infinity. So at least one of the one-sided limits is infinity. It could be both, but at least one is infinity, so it's the last picture on this sheet. All right.
The last one is infinity, right?
Yes, tends to infinity. As x tends to x0, the function value tends to infinity. It doesn't matter if both one-sided limits tend to the same infinity, the same direction. It's still discontinuity. Even if I have the graph something like this, it's still a discontinuity because it tends. It's the function value is infinity. The function is not defined here. It doesn't exist. All right. Let's try to go through those pictures. Oh, it did. He kept skipping around. I hope you can see the original. My original creations were actually in color, and so when printing, it becomes all gray, unfortunately. All right, so we have a specific function. I'm not going to tell you the equation, the formula of this function, because we will investigate functions like this later. So let's have a look at pictures without any formulas. Today we are not going to do too many calculations. but at least we can figure out some limits from sketches. So, A, limit as x tends to 0 minus of this function. 0 minus means from the left hand side, from the left. So it's the one-sided limit from the left. Look at the picture. As x tends to 0 from the left side,
Tends to be x0.
what is the function value when x approaches 0? X approaches 0. What happens to the function?
0 is minus something.
No.
Approach to 0.
X approaches 0 from the left. X approaches 0 minus. Look at this. X approaches 0 minus.
X must be less than 0.
Less than 0, but approaching 0. What happens?
Here. Infinite. Plus
You
infinite.
will kill me. Oh, you will kill me. Kill my foot. Alright, what happens there is the graph looks like this. Right? So as x approaches 0 from the left, this limb, x tends to 0 from the negative side. X tends to 0 from the left. What happens to the function at this time? What does the function do? So, okay,
Increasing or decreasing?
all right. Imagine the function graph is, let's say, a wire, a fixed wire, and what I have is, let's say, a balloon, and I'm walking along the x-axis towards 0, and my balloon is filled with helium, so it's always vertical, and the string is stretching. So I am walking towards 0. What happens to the balloon?
Higher.
Okay. Where does it tend? To what? To infinity. So the balloon is the function value. Alright. So it's simply plus infinity, the positive infinity, because look at the right hand limit. If x tends to 0 plus, so from the other side,
Minus infinity.
to minus infinity, right? In B, the limit, the right-hand side limit is minus infinity because the function simply plunges downwards. As I approach x, as I approach 0 from the right, so 0 plus from the positive side, I see the function values. So it's not a helium balloon anymore.
The peak is up to minus 2. The peak point.
Yeah, okay. All right. And then we have. Okay. So as I approach 0 along x-axis from the right-hand side, in this case, of course, I don't have a helium balloon. I might have something heavy, and it just falls down as I walk there. And I look at this vertical line and this vertically, well, hanging rock, perhaps. It just plunges down to negative infinity. Alright, so the left hand limit as x approaches 0, the limit as x approaches 0 minus is plus infinity, but the right-hand side limit as x approaches 0 plus from the positive side is minus infinity, the negative infinity. So the function value of f, the function value at 0, f of 0, what would you say? Not defined. The function is not defined, obviously, because we can't even say it's infinity, because then it must be both infinities at once. The function value is not defined. We don't say the function value is infinity because infinity is not a value. Infinity is rather a process of something becoming greater than whatever we might require. So the function f of 0 is undefined. The correct answer is undefined. The function is not defined when x is 0. D, the limit, as x approaches 0, again a specific expression. No, it doesn't exist.
Doesn't exist?
No, it doesn't exist. Because we have one left-hand limit, one value, positive infinity. Right-hand limit, negative infinity. They are not the same. So the function limit does not exist. There is no limit to this function because it simply goes separate ways. One part goes up, one part goes down.
For this, we should know, yeah, the direction of the limit. The left hand
Yes.
side or the...
Yeah, well, sometimes, yeah. For this exercise, yes, and for the next one, yes, and then for another one. Yes, you have to understand what one-sided limit means. So we actually have three kinds of limits. Right-hand limit, left-hand limit, and simply limit in general. Limit in general is only exists if both one-sided limits exist and are the same. Only if both one-sided limits are the same, which obviously is not the case for the situation when x tends to infinity, because infinity cannot be approached from two sides. So that definition is slightly different. But for the finite values of x, three kinds of limits, from one side, from the other side, and if they both exist and are the same, then we call it the limit, simply the limit. So the one-sided limits are a little bit less than a real limit. Almost, but not quite, from one side only. So it's like just like being in love, you know. One person loves the other doesn't love the first one, so nothing. But if they both love each other, then something, we might say, a limit happens. 12. 42. Alright, so the limit does not exist. So there are different phrasing, different, let's say, correct answers. Different correct answers. Limit is positive infinity, limit is negative infinity. The function is not defined at 0, and the limit at 0 does not exist. The function is not defined, the limit does not exist.
Wait, which one was it?
CD. C and D.
Yeah,
Because
C.
we are still investigating that 0. In A, B, C, D, we are investigating 0, the 0 situation. So one-sided limits might be infinity. The general limit in general does not exist because they are not the same. And the function itself is not defined. So there are actually, there are four things that can be investigated about any point from the domain. Any point from the domain, and we can tell these four things about it. Both one-sided limits, the general limit, and the value of the function. Sometimes function is not defined, sometimes limit does not exist, and sometimes a one-sided limit does not exist. For example, the square root of x is not defined for negative x, so I can't say x tends to 0 minus for the square root function. Okay, E, limit of f of x if x tends to 2. When x tends to 2, yes, when x tends to 2, the function value tends to minus 2. Besides, we can see that it happens from both sides. If x tends to 2 from the right, 2 plus, then the function value tends to minus 2. If x tends to 2 from the left-hand side, 2 minus, then the function value also tends to minus 2. Which means the function limit is this value. Generally, you simply see that usually, if the function is continuous, the limit is the same as the function value. So that's easy to see. If you see from the graph that this function is continuous for x is 2, then obviously minus 2 is that limit. The limit is the same as the function value. Sometimes, well, often. And finally, the equations of the as x tends to infinity. When x tends to infinity, what happens to the function? 0, both sides. So in both directions. If x tends to positive infinity, and also if x tends to negative infinity, the function value tends to 0. And the equations of vertical asymptotes. Asymptotes, remember, the lines for which the distance between that line and the graph of the function becomes infinitely small, but never 0, really, not 0. So the line which is approached by the graph. So the graph, the curve, the graph of the function tends to that line, closer, 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 never reaches it. Unhappy love. So the equations of the vertical asymptotes. A vertical line, the equation of a vertical line is x equals something. So one vertical asymptote is obviously x equals 4. That's the dashed vertical line. And the other vertical asymptote is actually the y-axis. The equation of that one is x equals 0, of course. On the y-axis, x is 0. So these are the equations of vertical asymptotes. We don't say vertical asymptote is 4. No. 4 is a number, asymptote is a line. A line cannot be a number. So we say the equation of the vertical asymptote x equals 4. So for all points on this vertical line, the x coordinate is 4. The y coordinate can be anything. Right. Number 2. Now this is a piecewise defined function. A very strange one if you can see. So there are some holes, some empty points, and then there are some quite large potato-like dots representing some other function values. I was unfortunately using a graphing program that wasn't very good at that time. I don't know why these points look like that. There was something wrong with it. I couldn't make it the way I intended. So they became very large. All right. So here we have 14 questions about this function. So the function is given by a graph. Now we have to try to see what the limits are. A. Limit as x tends to 0 minus 0. If we look at this graph and approach 0 along the x-axis from the left, well, okay, my right side, from your point of view, it's the left. The function value tends to 0. The right-hand limit b, if x tends to 0 plus, from the positive direction, 0. So this means this function value, this limit of the function exists because both the limits are the same, and we can see how they meet at the same point from both sides. So the limit of the function in C is also 0, and the value of the function is 0. So completely different from the previous example. I tried to make it on purpose, just like that. All right. The next one, E. When the function when x tends to plus infinity, to positive infinity, what do you think the limit of this function is? 3?
0. No.
Minus 2.
Something.
Minus 2. Minus 2. I didn't sketch the horizontal asymptote to make sure to point out that this function indeed tends to minus 2. I should have sketched in a horizontal asymptote to show that the function value actually tends to this value minus 2. But we can see that this graph, this function tends to minus 2 if x moves to the right in an unlimited fashion.
We should move the x.
X tends to plus infinity. E. X tends to plus infinity. It means we are moving along the x-axis in the positive direction infinitely. All the time. So what happens to the graph? What happens to my helium balloon or something? It tends to -2 in the second exercise.
The roof.
Yeah, that's the roof. Yes, that's the roof. There's some limitation. It can't rise higher up. Right. Exactly. Now f 2 plus the limit,
No limit.
right hand limit if x tends to 2 plus.
Can't be defined.
Why no limit?
Oh,
No, there is a
here.
limit.
Yeah, -6. Oh, I missed it.
Wait. It's not -6. 2.
2?
Look, find the y-axis. It's not the asymptote, it's not the dashed line. The y-axis. And now if x tends to 2, just find 2 on the x-axis. If x tends to 2 from the right,
Yeah.
the limit is 4.
4.
It's 4. If x tends to 2 minus from the other side,
6. No.
the same point.
4.
4.
Yeah.
So the limit of the function as x tends to 2 is actually 4, but the value f of x. Okay, see the piece of a function or the point has simply fallen off and is fallen down.
Oh, yeah.
So the function value is -5. 6, no. It's not 6, it's 5. Count the squares. Oh yes, this software actually, I was using it sometimes. It puts the numbers on the axis a little bit strangely. It has a strange manner of putting numbers on the axis, so you always have to check the number of squares. It's -5. It's -5. So f of 2 is -5. The limit when x tends to 2 is +4. So there's a jump discontinuity, obviously. Oh, sorry, the removable discontinuity. I could actually remove this discontinuity if I just picked up that black dot and plugged the hole on the graph. All right, x tends to 5. What the limit is?
-4.
-4, but f of 5
2.
is 2. So the limit of a function is not necessarily the same as the value of the function. In most cases, yes, but not in the situations where we are very sneaky and define those functions in special ways. Yes?
What about the I, the limits?
Which
Approach
limit?
to the 5, and then if it approaches to the 5.
The limit, no. When x tends to 5, when x tends to 5, where does the function go? Oh, it should have been 6. I didn't count the squares correctly. It should have been 6, because if you count the squares, it's actually 6, the dangerous point.
Oh.
It's my fault. So I should change it to x tends to 6. So I'm not sure that my computer will allow me to do now. So, alright, if x tends to 6, if we change the tiny 5 to a tiny 6,
Sorry.
what? This should be, oh, just for x, yes, because 1, 2, 3, 4, 5, this is 5, this is 6, this is 6. If x tends to 6, the function tends to this, see? The function to, actually, -4, to -4. So it's -4. But the function value is 2, because see, the point is there. It's taken out of this and put there. So it's 4, so it's 2. Yes. Okay. All right. Now, k, 3 minus minus 3 plus. So left hand limit minus 3, sorry, not 3 but minus 3. Minus 3. If x tends to minus 3, minus from the left. The left hand limit is
Plus
2, right. And if x tends to minus 3 plus, so the right hand limit,
It's 6? No?
minus 3.
Minus.
X tends to minus 3. 1, 2, 3, no. X tends to minus 3 from the right. Where does the function value go? Count the squares. If you have any doubts, count the squares. To find the coordinates, you can count the squares. So if x tends to minus 3 from the right, it's minus 1. The limit is minus 1. Now, obviously, the limit at minus 3 does not exist. The limit does not exist because there's the jump discontinuity. It's the jump discontinuity. But the function value at minus 3, the function value at minus 3, which one? Where the fat black dot is? Minus 1. The fat black dot is minus 1. So the function value is minus 1. So is the right hand limit, but the left hand limit is something else. So we have a jump discontinuity. And if we have, well, not here, but we have still some limits to consider, for example, x tends to 3. When x tends to 3, we could say again the one-sided limits are positive infinity, minus negative infinity. The total limit does not exist and the function is not defined if x is 3. It was not in the question, but worth noticing. Now, let's try to sketch an example. I'm saying an example because there are no strict rules. There are some 7 conditions. 7 conditions that must be fulfilled in our graph, but the rest is not defined. So the rest can be chosen as we like. Okay.
One question.
Yes.
Can you just draw the graph of the x absolute value?
X absolute value.
And from the limits of the x is 0.
X absolute value. X absolute value. If x is positive, then x absolute value is the same as x.
No, just in general. No, I mean like x can be anything. So like from negative.
Yes. So for negative x values,
Yeah.
for if x is positive, okay. The function x absolute value is x if x is greater than or equal to 0, naturally. And what happens if x is less than 0? How do we define the absolute value? Minus x. So this is y equals x, this part, but it's only good for the positive x value, so we only take this part. And for the negative values, we have this line. Y equals minus x, but we only use this function for negative x values, so it's this part. So it's a v, just like this. Or, after all, remember how we do the function absolute value. If the function is x itself, we could think, okay, the function y equals x is this. But if I have to take the absolute value of this function, I must fold this part.
I know. I just want to find the limit of the.
Oh, you want the limit?
Yeah.
So the one-sided limit is 0, both of them. The limit is 0, the function value is 0, no problem. There's no problem. There's no interruption, there's no gap. It's continuous. It's continuous. The function value is 0. And the limits are also 0 because as we approach 0 from either side, the function value, yes, it approaches 0. It's 0 there, no problem. All right, the sketch. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 0, 6, 6, minus 6, minus 6. Okay, so the limit as x tends to 0 plus, meaning right hand limit, of the function is minus 2. We don't know yet whether this point will be empty or black. So, alright, minus 2 as x tends to 0 from the right, so it's something like this. The approach will be like this. So I'm just sketching in the very end of the graph. Small bit of graph. So if x tends to 0 from the right hand side, the function value tends to minus 2. I just drew a very small arrow. Number 2, if x tends to 0 minus from the other side, the function tends to 1. Okay, so it will be from the minus side, the function tends to this. What next? 3. F of 0 is minus 1. Oh, somewhere else. So one-sided limit, empty point. One-sided limit, empty point. But if x is 0, then y is minus 1. So this is the full point. So the graph will approach this point from the left, this from the right, but actually the function value is somewhere else. Now number 4, if x tends to 2 minus, so to 2, x tends to 2 from the left hand side, the function value tends to positive infinity. So it should go up there. Alright, I will draw a vertical asymptote too. And I know that if x approaches 2 from the left, from the negative side, the function value tends to plus infinity. So it goes up there, should be up there. If, number 5, if x tends to 2 from the positive side, from this side, the function goes to negative infinity. That's what number 5 states. So it has to go down there. Again, very small arrows. Very small arrows. And what we still, if x tends to plus infinity, the function value tends to 3. The limit of the function is 3. So the roof thing, 3 is there. If x tends to positive infinity, the function is coming here. To 3. If x tends to positive infinity, going on and on and on, the function value approaches 3. And if x tends to negative infinity, the function value approaches 4. Okay, 4 is here, so to the negative side it would be there. And now, all 7? Yes. Now we should sketch the example of this graph, an example of this graph. So now we have fulfilled all the 7 conditions. See, 1, 2, 3, 4, 5, 6, 7 conditions are fulfilled. Now we need to complete the graph. The other function values are not important, so only these are. So it doesn't say anything about anything, so I could.
Yeah.
But for example, I could do it like this.
Yeah, that's what I think.
Because there was no mention of anything else. So I could be simple. I could draw something just like this, or I could be creative. Mathematicians like to be creative. So yes, for example like this. No problem. Or I could have drawn a smoother line, no problem with that either. Okay, what else? Now we have to this branch of the function, the ends are here and there, between 0 and 2, we have this branch of the function, this part of the graph. All right. Okay. Or I can draw a smooth one, no problem with that. So which would you prefer, smooth or wavy? Depends, it doesn't matter really. It doesn't really matter. So like this, and this will be more function-like, not so vertical, because we know that vertical lines are not good. Okay, very small. So this is the empty point, this is the full point, this is the empty point, and now we have this. There's nothing that says that an asymptote must never be intersected. It must never be reached in the infinity, but actually there's nothing to forbid us something like this. Why not? Sometimes the function fluctuates or oscillates before, well, it never reaches the asymptote, but as it strives towards infinity. So it could be like this, or it could be simply like this. So there are variations, of course, of that function. I could draw this part just like this. I could draw this part like this. I could draw this part like this. It's just one example. So nobody requires you to do fancy stuff.
That's not a function.
Yes, probably. This part is not, but the rest is, I think. Okay.
Identify whether it is function or not.
The vertical line test, remember, if it's a function for the same x value, it must not have two function values at the same time. The same x value cannot have more than one function value. Only one y value. So for example, I can write an equation for the circle. I can write the equation for a circle. X squared plus y squared equals radius squared if the center is the center of coordinates at the origin. It's not a function. This does not express a function. This does not describe a function, because for these x values we have two different y values. It is an equation of the circle, but this is not an equation of a function. This is not a function. This is not a graph of a function, because there are two different y values for the x values possible. So yes, because I was sketching freely, carelessly, because of my carelessness. At some points, this might not be a function if I was very strict and checked with the vertical line. The vertical line test is the one that we should use for graphs. If the vertical line intersects the graph at one point only at any given moment, then it's a function. Number 4. Determine the limits. How can we do that? Well, if we know, we could draw the functions, or we could just think.
If it's
The thing is better.
Yes, I agree. My foot hurts. Fortunately, I don't need my foot to think. Alright. Function A, we recognize that this is a quadratic function. We know that the graph is a parabola. We know that it is defined for all the x values possible. We know that it is continuous. We are very familiar with quadratic functions. So this is a continuous function, which means the limit is the same as the value.
So the a will be 0?
No. Minus 6. The
Yes.
function value. You put 0 into the function. So you put x tends to 0. All right, let's see what happens if we put 0 in the function. So we get minus 6. So this limit is minus 6. Many limits can be found by simply putting in the x value.
If it's constant.
If, well, yeah, if it's continuous. If it's continuous. B. We can see that this function is discontinuous at which point?
1.
X is 1. That's why we were practicing finding domains of the functions. We can never divide by 0. That's the main cause of discontinuities. Not the only one, but the main cause of discontinuities. So the disruption or discontinuity is at x equals 1, which means the function should be continuous at x tending to 4. So what?
3 minus 3. Minus 4.
Minus 4. Minus 4. 12 over minus 3. 12 divided by minus 3 is minus 4. So that's the limit. If we can calculate the limit, then we do it. Yes?
I couldn't get the main idea of the discontinuity and the continuity.
Discontinuity. Discontinuity, the natural kind of discontinuity is, well, just this, the main idea. From the equation, the discontinuity, first of all, happens if you have to divide by 0. You know that you cannot divide by 0. You know that when you are finding the domain, you look at division and you, first of all, you say, okay, those values for which we have to divide by 0 are excluded. Yes?
Question, in A, 6 or minus 6?
Minus?
Minus.
Я же не говорю минус.
So then you say that if the x is equal to 1, or
If x is equal to 1, then this function is not defined because you cannot divide by 0.
so it means it doesn't mean that it's
Discontinuous at 1, yes. If x is 1 at different points. So a function can be continuous at one point because it's a smooth line, but it might be discontinuous or interrupted or disrupted at another point. So here it's continuous, here it's continuous, here it is discontinuous. There is this gap. So in this case, in B, we see that x cannot be equal to 1 because we cannot divide by 0. So x is 1, at that point we have a gap, a disruption, a discontinuity, but not at 4. The limit is required when x tends to 4. So that's not a problem. We can find the function value. And so we have minus
3.
something, 4.
Minus 4.
Minus 4. Okay, C.
0.
0, when x tends to infinity, if we have to divide 5 by a very, very large, even larger, and even larger, we get a very, very small, smaller,
Close to 0.
close to 0. Yes, so the greater is the x value, the smaller the function value becomes. So 0, C is 0. When you have to divide, well, we don't divide by infinity, just like we do not divide by 0, but we can think of quantities of x being very, very large, tending towards infinity, increasing indefinitely, increasing without limits, or becoming small, small, decreasing, becoming infinitely small. Not exactly 0, but infinitely small. Now I have 4 interesting ones. D. X tends to 5 plus. So what is the limit of the function 2 divided by x minus 5? Obviously 5 is a discontinuity at that point because we cannot divide by 0. So x cannot be equal to 5, but generally x can tend towards 5. It might not be equal for the function, but it might tend towards 5. So can you figure out what those two one-sided limits are?
So it must be a plus infinity.
In D, yes, because if x tends to 5 plus, it means it tends to 5, but it stays greater than 5. And therefore, x minus 5 will be positive. Very, very small, close to 0, but positive. So it will be positive infinity.
And in E will be negative.
Yes, exactly. Because x tends to 5, but it remains less than 5. So x minus 5 is perhaps very, very close to 0, but still negative. So 2 divided by a negative 0, if you can imagine something like that. So in calculus we do things like this. If you can imagine negative 0, then 2 divided by a negative 0 will be negative infinity. So when we say in calculus divided by 0, divided by infinity, we don't really mean it. What we mean is we divide by something that is infinitely large, it's indefinitely or as large as we want. Or if we say divide by 0, we say we divide by something that is very, very, very small, very, very close to 0, tending towards 0, but not necessarily being 0, approaching 0. Like the famous paradox, I can approach the window, but I can never reach it, because when I have covered half of the distance, then half still remains, then I cover half of what remains, and half of that still remains, and so on. So I will never ever reach the window. So that's what happens when we think x tends towards 0. We cannot divide by 0, but we do divide by x which tends to 0. Something like that. All right, F and G. Tricky questions.
This the last one. F and G.
Yes.
Tricky.
The same as the previous.
Tricky.
Tricky. Okay.
Infinity and infinity.
Minus
Positive, negative.
plus
X tends to minus 2 minus 5 over x squared minus 4. And the other one, limb, x tends to minus 2 from the right hand side, 5x squared minus 4. Okay.
Positive and positive.
Positive first. Is the positive.
So which one is positive, which one is negative? Or maybe both are the
Both
same.
of them are positive.
Both positive infinities.
Positive infinity.
Why?
Because we have x squared, everything that's squared is
Um,
positive.
Yes, but
Except 0.
if I want to know whether I have to divide, I don't have to divide 5 by x squared. I have to divide 5 by x squared minus 4. I'm not dividing by x squared. So what we have here is I have to understand whether this is positive or negative. Is this positive or negative? Positive or negative? This one?
Positive and positive. Because
It's like 5 divided by 0, 0, 0, 1.
am I right?
No.
What was your answer?
Both of them are positive.
No.
One is positive, one is negative.
This is positive. Why? Because, understand, this is a negative number, negative minus 2. If x tends to minus 2 from the left,
Still,
it means the absolute value, the modulus of x is greater than 2. So the square of x will be greater than 4. The absolute value, the modulus, here is greater than 2. Square greater than 4. So this is the positive infinity. On the other hand, if I approach minus 2 from the right hand side, it's, you see, the absolute value, the modulus of x is less than 2, the square is less than 4, so this will be minus infinity. Got you. Alright. Now 5 is sketching the graphs indicating the discontinuities and the types.
I just wanted the first one.
The first one, you don't know what it looks like.
I have some idea, but still.
All right, number 5.
It's just like 1 or...
It's just, it's, yeah,
It's a
like,
one. One
like,
minus one.
like
One minus
1. 1 or minus 1?
Yeah, just like program, like 1 minus 1, 1 minus 1.
So, what do you think? You think this line with holes? No? So, remember, if x is positive, then x absolute value, the modulus of x, is the same as x. So, for positive values of x, this function, 5a, will be equal to 1 for positive values of x. Positive values of x, the function is equal to 1.
Yeah.
Okay. For negative values of x,
Also 1.
No, minus.
no,
Minus.
negative, minus 1, because the numerator is positive, modulus, and the denominator is negative, so it's minus 1. What about 0?
Undefined.
Undefined. You cannot divide by 0, so it's undefined. The function is not defined there. So we see that this graph consists of two half lines without the points, actually. And so, what kind of discontinuity is it? It's the jump discontinuity. It's the jump discontinuity because the one-sided limits here are different. The one-sided limits are not the same. So this is the jump discontinuity, type 1. One over x squared in B. What about that? I remember 2 days ago I left it for yourselves to discover.
Yeah.
So 1 over x squared is
That's
not
pretty-
really a hyperbola, but at least slightly similar. And of course it's both sides are positive because it's an even function. So this would be type 2 discontinuity because both the one-sided limits are infinity at 0, at x equal to 0. So you see, we will need sketching and graphs more and more and more. We need those graphs sometimes simply to understand what's going on, sometimes to investigate those functions, sometimes to find the areas when we integrate next semester. All right, x divided by 2 for all x values except for 2, and 0 for x equal to 2. C function. C function. X divided by 2 is a linear function. It's 1 over 1/2 x, which means this is the slope, this is the gradient. So it is 2 steps right, 1 step up. 1, 2, 1, 1, 2, 1. So this line for all values except for x equal to 2. So this is a hole at 2. 2, 1. Right, there's a hole. But if x is 2, there's an extreme definition 0 for x equal to 2. So this point. Now we can see that one-sided limits are equal. So the limit of this function is 1 if x approaches 2. But there is this discontinuity, which was called what? Removable, because I can take the plug and put it into the hole. D. Ooh,
3 parts.
3 parts. Shall we do it? 3 parts. So minus infinity, minus 2, minus 2, 2, 2 plus infinity. Okay. 1, 2, 1, 2, 0, 1, 2, minus 1, minus 2. So I will actually sketch the boundaries for the graphs so that I can see which part I should take at minus 2 and at 2. So if x is less than minus 2, we have the graph minus x minus 1. Okay, minus x minus 1, minus x minus 1 means 1 right, 1 down, 1 right, 1 down. So it would be this one, But I need this line only for x values less than -2. So it will be this half line at this moment empty point.
Less than 1.
For less than -2, yes. Less than -2. Now, between -2 and 2, we have x squared minus 4, which means the vertex of the parabola is 1, 2, 3, -4 on the y-axis. Now, 1, 1, 1, 1, 1, 3, it's there, and there. So I sketch the parabola y squared minus 4 for the central part. That's easy to do. And these points both count. And then 4 over x minus 2. Now it's a bit difficult because it's a hyperbola which has been moved. How? The shift. So it's a hyperbola 4 over x, but shifted 2 units where? No, right. Remember f of x minus a. So if it's x minus 2, it means 2 units right. 2 units right. Okay. So I can imagine that this is the y-axis and try to 1, 2, 1, 2. This point, 1, 2, 1, this point, so I can sketch the graph like this. And we can see that because it's shifted 2 units right, the vertical asymptote, instead of y-axis, the vertical asymptote is this one. Because it's shifted 2 units right, we simply have to think about what happens. So we have 2 discontinuities, obviously, for this graph, for this function. One is a jump discontinuity, type 1. Everything is finite. And type 2 discontinuity because the right-hand limit is infinity. So this is the first one is type 1, and this is type 2. This is type 2. And finally, one more. One last function. Find the value of the coefficient k for which the function is continuous. How on earth can we do that?
Just make 1 to each and make it equal.
Yes.
Cool. So x is 1.
So if x is 1, if we want the function to be continuous for anything.
So it's 1.5, right? Okay.
Yes. Yes. K is 1.5. So to do this, to find the value of the coefficient, to make the function continuous without gaps like this, we have to make sure the function value at point x is 1 is the same. Of course, if x is 0, the function, if x is 0, everything is okay. Because at that point, we have the quadratic at that point, right? Yes. So the thing is, we have to say, all right, if x equals 1, the function value is 1, and then we require that in the other fragment of the graph, in the other part of the graph, that function value at 1, if x is 1, is also 1. And we see that 1.5 minus k times 1 squared has to be 1. It has to be equal to 1. So this means that the value of k is 0.5.
Must be equal to 1
because the other part, because 1 over x is 1 for x is 1. We want to join the two parts. See, if if at x equal to 1, one part looks like this, and then the other part looks, well, something else. We have this continuity. What we want to do is to make these points, put these points together. So for one part, I know that on the left-hand side, whatever the graph is, they are not the correct graphs, of course. On the left-hand side, I have to understand that there is a certain value. When x is 1, I look at the function, I see if x is 1, then the function value is 1. I can see it from the formula. Okay, so this is a set value. And now I say, okay, I want this part to be 1 also at this point. So I say 1.5 minus kx squared has to be 1 for x equal to 1. And this is how I get the k value. So this is a little bit of logical reasoning. Not too much difficult mathematics, but you definitely have to think, people, think. Okay, that's it for today, I see. I think so, at least, if there are no questions. If there are, I'm still sitting down. In general, if x and this. Well, it should be, if it exists, then it should be the absolute value. Oh, this thing. It should be, yes. If the function exists and is a, if x tends to something, then obviously the limit of the absolute value of that function should be a absolute value. If you see, if there's no gap, then when you reflect the bottom part upwards, there's no gap. Nothing gets broken up.